Okay, so we want to cover this topic called logistic regression, which is one of the algorithms that is available to us in Weka. And although it's called regression, it's actually a classification algorithm. So usually we don't use the word regression, but we're calling it logistic regression anyway. Now, if you remember, we did talk about regression, and here's an example of where we might use regular regression. We have two numeric variables, weight and size, and then we try to fit a line that will model the relationship between weight and size. So what we mean by model it, of course, is that if we put in a particular weight, we will predict a certain size. So we did this before. And this was an example of when we did it when we're working with two numeric inputs. But like I said, for a logistic regression, it's going to be a classification algorithm, and usually we're going to have a numeric input and predicting a class in the output. So in the video in this example, we're going to have weight, and then we're going to, and these are going to be mice, and we believe that there's a relationship between weight and whether the mouse is obese or not. And we're going to have some mice with very low weights, and this mouse has a very low weight, but it's not obese. And this also has a low weight, it's not obese. This has a low weight, it's not obese, but this one has a fairly low weight, that is this one here, this mouse, but even though the weight is pretty low, still it's obese. And this one has a slightly higher weight, but it's not obese. So we have weight on this axis, and then we're either going to have obese or not obese. So the point here is to notice that we don't have any dots that have heights other than this level and this level, because this is a class scenario. So we have just two classes, and actually there's no natural order for these either. Like when we have numbers, we have a natural order. We put the lowest number first and the highest number later. But obese and not obese, we could have just switched these. There's no natural order for these. They're just classes. Now we still could try to sort of fit a line to this data. We could do that, but that is generally not going to work that well. And instead, we're going to do what's called logistic regression. So instead of trying to fit a straight line, we're going to fit an S-curve. Now, we saw an S-curve recently in our class. So this is what I mean by an S-curve. And we saw this kind of curve. It's called a logistic curve in this video, but it's also called a sigmoid function, which is what we used when we were doing neural networks. So this function is very popular to use, and it's used many places. It has certain interesting properties, and so it's attractive to use in many different applications. So, of course, this has nothing to do with neural networks, but we are using this function. Like, for example, suppose, we had a straight line function. We might use a straight line function in some other application. Doesn't mean that two applications have anything to do with each other. So just because we're using this S-curve here doesn't mean it has anything to do with a neural network. And it's called a logistic curve here. And as I said, we also called it the sigmoid curve, or just an S-curve. Now, before we go and check logistic regression, let's just remind ourselves that oftentimes we're predicting an output, and we have many inputs, not just weight. We might also have this as another variable. So if we want to draw it, we might need a third dimension like they've tried to put in here. And so you could have, you'd measure some, I guess maybe this is a mouse, I don't know, some mouse's weight, and then their blood volume, whatever this is, and then you'd get a size. So we could have two variables as inputs, or of course we could have many more variables. You deal with many input variables in your projects, and of course you can't graph them like this anymore if you go beyond two input variables. So at the end of this video, he's going to say, okay, we have this logistic curve here, which we're going to use to fit the data, just like we would have a straight line curve to fit this data. Now, when we studied regression, we didn't really talk about how to choose the best line, but this looks like a pretty good choice for this data. I could try and draw something like this, or maybe something like this, and thus don't seem as good as this line to fit the data. So there's a concept of called the least squares, which we actually talked about. We talked about the sum of the squares of the error. So remember we talked, or the sum of the squares of the deviation. So we could talk about this picture. So the deviations are colored in blue, and we want to choose a line. Like I said, I could draw a line like that. I could draw a line like that. So we want to choose a line which is going to have the least of these deviations. And we talked before about the fact that we don't consider just the deviations, but rather the absolute value of the deviations or the squares. And usually it's the squares, not the absolute values. But anyway, whatever it is, if it's a square of the absolute value, whatever it is, we want to have the least. And of course, a different line is going to generate a different set of blue errors. And we want to choose the line which has the least of this kind of error, which we call the sum of squares. These are sometimes, we call them the deviations. They can also be called the residuals, because they're kind of what's left over after you use the line. So we had that criteria for choosing the best line. Now we want to go to this picture, and we're going to say, okay, let's try and fit an S-curve to this data, because we're going to use this S-curve to predict the data. For example, when the weight is, say, here, let's say right here, then we're going to predict something like, well, let's say it was right here. So we're going to go up to here and over, and that's going to be our prediction. And then basically what we're going to do is we're going to say, well, if the prediction is closer to the is obese, then we're going to say it's obese. And if it's closer to the is not obese, for example, if we had a weight here and we went up and over to here, that's closer to the is not obese. So anyway, the point is we're going to use this as a predictor. Now, we're going to be using S-curves instead of trying to fit a straight line. But we are still confronted with which curve to use. Which one should we use? Like this is one S-curve, but he's going to show us other possible S-curves. So here's maybe this was the first S-curve, and then another possible S-curve, and another possible S-curve. And which of these S-curves fits this data the best? That's what we have to figure out. And we need some kind of criteria to decide. And it turns out that we're not going to use the residuals or the deviations from this line. That's not going to be the way we're going to decide between the best curve, to find the best curve. So is this better than this? Is this better than this? Which one is the best fit for our given data? So if we have this given data, maybe, who knows, maybe the middle one is better. And if we had some other given data, maybe you had more stuff over here, maybe the black one would be better. Now, in this video, he's going to introduce us to a very interesting criteria for choosing the best curve amongst all of these different possible curves. It's called the maximum likelihood estimate, or it's called we're using something called the maximum likelihood. We're not using that concept of residuals. So what we want to do is we want to measure how well does this curve predict this data, and then we'll talk about another possible curve. For example, how well does this curve predict this data, or how well does this curve predict this data? And that's the criteria we're going to use. So that's not the same thing as the residuals or the deviations. How big are the deviations? It's not the same concept, but it sounds very natural. How well does this curve predict our red data? How well does this curve predict our red curve data, and so on. So how do we measure how well one of these curves predicts our data? Well, let's see. For this particular piece of data, what does this black curve do? Let's just explore this idea quickly right now. So what does this black curve do? So for this particular data, now this mouse is actually not obese. So regardless of what the model predicts, the truth value, or the true value, or the actual state of the mouse is that it's not obese. The model may predict that it is obese, and we've seen that many times when we look at the confusion matrix. We've seen many times where the model makes the wrong prediction. But so the model may predict that it's not obese, but that it is obese, but it doesn't matter. I mean, in reality, it's not obese. So let's see, what does this black model, black dashed line, predict about this mouse? Well, this mouse has the weight over here, so we go up here, we go straight up, we go to here, and over to here. Well, it's going to predict basically that it's obese, right? We would say, oh, it's very close to the obese, so we're going to predict that it's obese. So basically, we should say that this black model makes first of all the wrong prediction for this actual piece of data, and we can even quantize how wrong it is. So I'll give you a little hint. What we're going to do is we're going to call this scale here probability. So if it's down here, it's going to be 0% chance that it's obese, and if it's, or let's say here, if we have something here which goes here, which goes here, that's going to be like maybe 10%. So we're going to say there's a 10% chance that it's not obese, and therefore a 90% chance that it is obese. On the other hand, if we had something over here, then it's going to be up here, and it's going to be like over here. So maybe there's a 95% chance that it is obese, and therefore just a 5% chance that it's not obese. That's what this curve is doing. So let's just look at this one dot here. So first of all, we'll notice that it's not obese. This is not an obese mouse. But what does the curve say? So if we go up to here and we go over, it says there's about a 95% chance that it is obese. It's almost right there at obese. So there's a 5% chance that it's not obese. So this, we're going to take the 5% because this is not obese. So we want to consider what the curve says about that. And there's only a 5% chance associated with that. Then we're going to do the same thing with all of these dots. Let's do one more. Let's take this dot here. So this dot here is also not obese, but what does the curve say about this dot? Well, right here it's probably like a 99% chance the curve is saying that it is not obese, and therefore like a 1% chance that it is obese. But this is actually not obese. So it says there's a 99% chance that it's not obese. So what we're going to do is we're going to take, this one was, I forget what I said, maybe 5% chance that it's correctly classified, and this has a 99% chance that it's correctly classified. We're going to do that for each one of these, and we're going to multiply all of those together, and that's how we're going to measure that product of all of those is going to tell us how good this black curve is. Then we'll do the same thing with each of these curves, so to speak. We can't do that because there's an infinite number of curves, but that's the idea. We're going to do it with each of these curves, and then the one that has the highest means it's doing the best. So we will choose that curve. So that's the idea behind the maximum likelihood principle. So let me just make this a little bit more concrete. So, okay, so this one is not obese, and let's do this for the black curve. So this one is not obese, and what does the black curve predict about it? I'd say the black curve predicts about 99% chance that it's not obese, right? Because if you go here and you go to the height, it's probably even 100% chance that it's not obese, but let's just say 99%. So we get a 0.99 as our first, and then we get times, I want to put times, and then Okay, what about this one? This one is probably almost the same. Maybe let's just change it because maybe it's rising a little bit. So let's say this one is 0.98. 0.98 for the second mouse. And then this one is jumping up just a little bit. So let's call it, say, 0.95. So I have to put times 0.95. So this is telling us how good the curve is doing for these three pieces of data. It's doing very well. Basically, it's predicting them very well. But then we get this one up here. Now the curve, I think the weight is about here. The curve only predicts, say, let's be generous and say it's, I'm going to just overshoot it. I'm going to say it's 90% chance that it's not obese, but it actually is obese. So it's only a 10% chance that it is obese. So we're going to put that here, times 0.10. So this is telling us that it didn't do a good job. We're taking this and multiplying it by 0.1. So it's reducing the size of this string that we're calculating because this didn't do a good job. Okay, then we go up to this one, and we go here. And this one maybe is about 0.5 on both sides, whether it's obese or not obese. So we add in a 0.5 there. So it didn't do a great job, but I don't know, whatever, 0.5. And then we go to the next one, which is here. So sorry, here. Or wait, did we do that one? Yeah, we did that one. Now we go to here maybe. So this one has about a 90% chance maybe that it is obese. But what's the chance that it predicted correctly? Correctly is not obese. So it only was about a 10% chance that it was correct. So we add in times 0.1. So we do this with all of these, and then we multiply this out, and that's going to say how good this black curve was at predicting these points. And then we could do the same thing with this curve, and maybe it does better, or maybe it does worse. That is, maybe the product of these things when we use this curve is more, it's doing better then, or it's less, it's doing worse. And so we then want to choose the curve which does the best. And that's how we select which of these curves should we use. And that's the idea behind the maximum likelihood principle. Okay, let's watch.
If you can fit a line, you can fit a squiggle. If you can make me laugh, you can make me giggle. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about logistic regression. This is a technique that can be used for traditional statistics as well as machine learning. So let's get right to it. Before we dive into logistic regression, let's take a step back and review linear regression. In another StatQuest, we talked about linear regression. We had some data, weight, and size. Then we fit a line to it. And with that line, we could do a lot of things. First, we could calculate r² and determine if weight and size are correlated. Large values imply a large effect. And second, calculate a p-value to determine if the r...
Okay, so we didn't talk that much about this r² because we didn't get into regression that much. But r² just measures how good the line fits the data. And the p-value tells you, like, if you have many variables, you can use the p-value to decide which variables are important.
Statistically significant. And third, we could use the line to predict size given weight. If a new mouse has this weight, then this is the size that we predict from the weight. Although we didn't mention it at the time, using data to predict something falls under the category of machine learning. So plain old linear regression is a form of machine learning. We also talked a little bit about multiple regression. Now we are trying to predict size using weight and blood volume. Alternatively, we could say that we are trying to model size using weight and blood volume. Multiple regression did the same things that normal regression did. We calculated R squared, and we calculated the p-value.
So you can watch his videos.
And we could predict size using weight and blood volume. And this makes multiple regression a slightly fancier machine learning method. We also talked about how we can use discrete measurements like genotype to predict size.
So here the input
If you're not familiar with the term genotype,
numeric.
Don't freak out. It's no big deal. Just know that it refers to different types of mice. Lastly, we could compare models. So on the left side, we've got normal regression using weight to predict size. And we can compare those predictions to the ones we get from multiple regression, where we're using weight and blood volume to predict size.
Okay, now we didn't talk a lot, or maybe almost not at all, about how to measure performance when the output variable is not numeric. We didn't consider numeric variables. So that's another, we have to think about it differently. We don't use a confusion matrix. So there's just another idea, which is probably a natural idea, on how to measure how good the model is if the output variable is numeric.
Comparing the simple model to the complicated one tells us if we need to measure weight and blood volume to accurately predict size, or if we can get away with just weight. Now that we remember all the cool things we can do with linear regression, let's talk about logistic regression. Logistic regression is similar to linear regression, except logistic regression predicts whether something is true or false instead of predicting something continuous like size. These mice are obese, and these mice are not. Also, instead of fitting a line to the data, logistic regression fits an S-shaped logistic function. The curve goes from 0 to 1. And that means that the curve tells you the probability that a mouse is obese based on its weight. If we weighed a very heavy mouse, there is a high probability that the new mouse is obese. If we weighed an intermediate mouse, then there is only a 50% chance that the mouse is obese. Lastly, there's only a small probability that a light mouse is obese. Although logistic regression tells the probability that a mouse is obese or not, it's usually used for classification. For example, if the probability a mouse is obese is greater than 50%, then we'll classify it as obese. Otherwise,
so that should be familiar to you. If you recall back in naive Bayes, we had this concept of a cutoff value. So here, we're using a cutoff value of 50%, which seems very natural. That is, if the mouse weighs somewhere up here, the prediction is going to be about 80%, for example. And so we're naturally going to say, oh, it's higher than 50%, so we're going to say that this mouse is obese. So we're using this cutoff value of 50%, which seems very natural, but we could adjust that also.
We'll classify it as not obese. Just like with linear regression, we can make simple models. In this case, we can have obesity predicted by weight, or more complicated models. In this case, obesity is predicted by weight and genotype. In this case, obesity is predicted by weight and genotype and age.
So what he's saying is that for logistic regression, you can have more than one input variable. And in fact, the input variables don't have to be just numeric like weight and age. It could be genotype, which is not numeric. It's a categorical variable.
And lastly, obesity is predicted by weight, genotype, age, and astrological sign. In other words, just like linear regression, logistic regression can work with continuous data, like weight and age, and discrete data, like genotype and astrological sign. We can also test to see if each variable is useful for predicting obesity. However, unlike normal regression, we can't easily compare the complicated model to the simple model, and we'll talk more about why in a bit. Instead, we just test to see if a variable's effect on the prediction is significantly different from zero.
So that's this idea of the p-value, and we didn't get to talk about that, but you can study that in regression.
If not, it means that the variable is not helping the prediction. Psst. We use Wald's test to figure this out. We'll talk about that in another StatQuest. In this case, the astrological sign is totes useless. That's statistical jargon for not helping. That means we can save time and space in our study by leaving it out. Logistic regression's ability to provide probabilities and classify new samples using continuous and discrete measurements makes it a popular machine learning method.
Okay, so let's just take note of that when we use logistic regression, we can get a class as the output. We can say it is not obese or it is obese, but we also get these probabilities, which is kind of interesting. We get both of these. We get a probability like 90%, and then since we have a cutoff, we can say it is obese. That is, if we have a 50% cutoff, then we can say it's obese. So we not only get the probability, but we also get the class. So having those probabilities can be useful.
One big difference between linear regression and logistic regression is how the line is fit to the data. With linear regression, we fit the line using least squares. In other words, we find the line that minimizes the sum of the squares of these residuals. We also use the residuals to calculate R squared and to compare simple models to complicated models. Logistic regression doesn't have the same concept of a residual, so it can't use least squares and it can't calculate R squared. Instead, it uses something called maximum likelihood. There's a whole StatQuest on maximum likelihood, so see that for details, but in a nutshell, you pick a probability, scaled by weight, of observing an obese mouse, just like this curve. And you use that to calculate the likelihood of observing a non-obese mouse that weighs this much. And then you calculate the likelihood of observing this mouse. And you do that for all of the mice. And lastly, you multiply all of those likelihoods together. That's the likelihood of the data given this line.
So I simplified the concept of likelihood just a little bit, but it doesn't matter. It's basically what I said.
Then you shift the line and calculate a new likelihood of the data. And then shift the line and calculate the likelihood again. And again. Finally, the curve with the maximum value for the likelihood is selected. Bam! In summary, logistic regression can be used to classify samples, and it can use different types of data, like size and/or genotype, to do that classification. And it can also be used to assess what variables are useful for classifying samples, i.e., astrological sign is totes useless. Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more, please subscribe. And if you have suggestions for future StatQuests, well, put them in the comments below. Until next time, quest on. We're in Hawaii. I'd be sitting on the beach in the shade of a tree, watching StatQuest.
Okay, I just want to reemphasize one point, and that is for this one, or let's say, sorry, this one, for this mouse, so it weighs about this amount. So if we go up to here, it's like 50%, or maybe it's whatever, who knows what it is, maybe it's 48%. So let's say it was 48%, then that would be, this number here would be 0.48. And then if we use the cutoff of 50%, we would say, whatever this was, I forget, what is that? Is that not obese or is obese? We'd say it's not obese. So if we use that curve, we go over to here, we'd say, oh, it's not obese. Now it happens to be obese. But anyway, we would predict that it's not obese, and that's because we're using the cutoff of 0.5. But we might choose to adjust the cutoff to change it. And we'll talk about that in the ROC discussion next.